We're going to find the general solution of the second order linear differential equation with constant coefficients y double prime minus 10y prime plus 25y equals 0. If you did not see the previous lesson, this is going to be rough. If you did, it should be pretty straightforward. We're going to start with the auxiliary equation, which in this case is m squared minus 10m plus 25 is equal to 0. You may know this factors as a square trinomial, or it is a trinomial square, I should say, that factors into m minus 5, the quantity squared, and it equals 0. You should keep the structure of an equation. Let's practice good math here. And we find that m is equal to 5 repeated. From previous information, we know then that y is equal to c1e to the 5x plus c2x e to the 5x. Yep, that's it. We're moving on. Next example. 2y double prime minus 3y prime plus 4y is equal to 0. Our auxiliary equation is 2m squared minus 3m plus 4 is equal to 0. Can we factor this? 2 times 4 is 8. Factors of 8 do not add up to 3. I'm going to say no. So we're going to use the quadratic formula. As I said before, if you're a little rusty on the quadratic formula, make sure you work on it a bit, because it might show up a couple of times, and I've seen people kind of flub it at this point, and that's not something we need to flub. M equals negative 3 plus or minus the square root of 9 minus 32 all over 4. Remember that 4 divides into both the 3 and the radical. This is going to give us negative 3/4 plus or minus the square root of 23 over 4 times I. That's a complex root, or 2 complex roots for the auxiliary equation. Therefore, y is equal to e to the negative 3/4 x, that's alpha in the previous video, but that's the real part, that becomes the coefficient in the exponential. And then c1 times the cosine of beta x, the imaginary part. So square root of 23 over 4 times x, plus c2 times the sine of the square root of 23 over 4 times x. Good news. Those arguments in the sine and cosine will always match, and they'll always be the imaginary part, and that is the solution. Next up, we have a third order differential equation. d3x dt3 minus d2x dt2 minus 4x is equal to 0. So our dependent variable is x, our independent variable is t. We have not seen a third order auxiliary equation, but if you just took a guess at what it was, you'd probably be right. In this case, it's m cubed minus m squared minus 4 is equal to 0. This isn't easily or readily factored. This would require some polynomial theory, and in a case like this, I'm going to recommend that you use some sort of technology, a calculator, a computer, or something along those lines. I would tend to use wolframalpha.com, and that's exactly what I've done to get the roots of the auxiliary equation. I have m equals 2 and negative 1/2 plus or minus the square root of 7 over 2 times I. I'd like for you to, at this moment, go ahead and pause the video, write down what you think the solution is. You won't see the little tile that says pause the video, but go ahead and pause the video anyway. Did you pause it? I'm going to get the solution. X is, I'll put x of t just to be fancy here, equals c1 e to the 2t plus e to the negative 1/2 t times the quantity of c2 cosine square root of 7 over 2t plus c3 sine square root of 7 over 2t. How'd you do? That's all those style of examples that we're going to do. You'll notice as we move through the chapter that doing all of this now becomes step 1. We're going to pile stuff on top of it when we have non-homogeneous differential equations. Before we get to that, though, we're going to look at a couple of special second-order differential equations. One of them is y double prime plus k squared y is equal to 0, and the other is y double prime minus k squared y equals 0. And k is a real number, so the plus is what you think it is, and the minus is what you think it is. The auxiliary equation for the first one is m squared plus k squared is equal to 0, and that's going to give solutions m equals plus or minus k times I. Based on what we've seen, we know that this is going to be y equals c1 times the cosine of kx plus c2 times the sine of kx. And it's just kind of a useful thing to know that when you have y double prime plus some number times y is equal to 0, then your solution contains a sine and a cosine in it. For the other one, the auxiliary equation is m squared minus k squared is equal to 0, and whether you factor this or add k squared and square root both sides, we're going to get m equals plus or minus k. So this becomes y equals c1e to the kx plus c2e to the negative kx, which doesn't really look interesting at first, but given particular numbers for c1 and c2, this can actually be represented using hyperbolic functions. I'm going to say recall, just in case you have actually seen hyperbolic functions. The hyperbolic cosine of x is e to the x plus e to the negative x over 2. The hyperbolic sine of x is e to the x minus e to the negative x over 2. I'm not going to get into what all these are. Either you've seen them or you haven't. If you haven't seen them, well, hey, here are two functions that show up as particular sums and differences of exponential functions. If you have seen them before, well, then you've seen them before. Now in this general solution, y equals c1e to the kx plus c2e to the negative kx, if we were to let c1 and c2 both be 1/2, then this would give us the hyperbolic cosine. If we let c1 be 1/2 and c2 be negative 1/2, we would have the hyperbolic sine, which are linearly independent solutions. And so these definitions, together with this form of a solution, would actually give us y equals c1 times the hyperbolic cosine of kx plus c2 times the hyperbolic sine of kx. I wouldn't expect you to produce these solutions. It would be fine if you did. They're as appropriate. But if you ever see them running around, I want you to know why they show up, and they show up because they're special sums and differences of particular exponential functions.